What are the oldest rocks on Earth? I was joined by Jesse and Chris from the PlanetGEO podcast this week to talk about Earth's oldest rocks. And in the part 1 video, we talked about the oldest rocks on Earth and how we determine their ages. And in this part 2 video, we're going to talk about what implications the oldest rocks on Earth have for our understanding of early Earth, like the moon forming impact, or when Earth first got oceans, or its first crust, or even the first life on Earth. So stick around for this part if you're interested in that, and make sure to check out part 1 to understand what the oldest rocks are that we're talking about in this video and how we determine their age, how we date them using radiometric dating. So now let's jump into this conversation.
So welcome back to our discussion about Earth's oldest rocks. We just had our part 1 to this discussion over the list of some of Earth's oldest rocks and how they formed and how we date them and isotope dating and all of these things and how they've been deformed over time and how we can tell that over on part 1, which is up on my channel. So go check that out if you haven't seen it yet. And now we are going to switch gears into talking about what Earth's oldest rocks tell us about earliest Earth history. So we kind of just transitioned our discussion into this very, very interesting part of our previous discussion on Earth's oldest minerals. These are zircons. And we talked about how these typically form in felsic or granitic rocks, meaning that they form in continental rather than oceanic crust. And we talked about this caveat of, but continental crust typically requires plate tectonics to form. And plate tectonics is often suggested not to have started until around 2.5 billion years ago, when these very, very old zircon grains are dated at over 4 billion years old. So how did these zircons form? Was it in continental crust? Was continental crust forming over 1 billion years before we thought it started? Or did it not involve plate tectonics back then? What do we think around that, whole topic?
Oh man, this is
Jesse,
Pandora's box.
Where do we begin?
Rich, I'm curious. Okay, so what is your opinion about the start of plate tectonics? What is your thoughts on this debate, maybe?
This is something that I have talked a lot about, maybe by accident on my channel, because I made videos very early on about how plate tectonics began and how differentiation began on early Earth, and how that started to form continental crust because more felsic stuff was being differentiated out of this more mafic stuff. And we got the differentiation between mafic ocean crust and, more felsic continental crust. And then these pods started forming because early plate tectonics was happening and they were bumping into each other because oceanic crust between them was subducting underneath them, kind of like what happens today, but on a smaller scale. Then later, I was contacted by somebody who's more an expert in plate tectonics than me, who also does YouTube stuff. His name is Stephen Bauman, and we made a great video together about how not all tectonics involves plates. And he talks about this hypothesis that plate tectonics didn't actually begin until around 2.5 billion years ago. And before then, there were other tectonic regimes like drip tectonics, which we talk about, and other lid tectonics. And we talk about all that. But he does mention that there are, different ideas about when this all started. And one of the things that complicates these theories of it starting later is the fact that these zircons are present so long ago. So I don't know. I have multiple competing ideas in my head.
Yeah. It becomes philosophical a little bit in this debate of when did plate tectonics begin? Because it's kind of like, well, what do you need for plate tectonics? Does one subduction zone on Earth mean plate tectonics? Most people would say, no, not really. It could be mobile lid tectonics, or the lid is breaking. There's like more than one plate. But is 2 plates plate tectonics? Or do you need 30 plates to be plate tectonics? Like, this is a really it's like a buffet table of stuff that you can pick and choose what you want in this debate. So it gets really complicated really quickly. Some people would argue vehemently that plate tectonics did not start until 900 million years ago. Some people would argue, myself would argue, something akin to plate tectonics was active 3.5 billion years ago, 3.6 billion years ago, and maybe not before that. Some people would argue plate tectonics has been active since 4.3 billion years ago based on Jack Hill zircon data. I'm not sure there's a unique solution to this debate. And this is an age-old debate that's been going on since the 60s.
Okay, but Jesse, regardless of when plate tectonics began, whether it was 900 million years ago or 2.5 billion years ago, how do you get zircons that are significantly older than that are concentrated in continental crust? Right.
Yeah.
So, go ahead.
Thank you,
what
Chris.
Are your thoughts on
Thank
that?
you very much for bringing us back home. Okay. So zircons crystallize in broadly rocks that are continental crust-like, but we don't need plate tectonics to form those types of rock. Those aren't unique. There are zircons on Mars. There are zircons on the moon. So zircons can form from not subduction zone magmas, basically.
Jesse, what you're saying is plate tectonics concentrates zircons. Right? The formation of continental crust.
Yeah, that's right. Most rocks formed in a volcanic arc and plate tectonic setting will have zircon-bearing rocks in them. Iceland has about 15 or 25% of the rocks in Iceland have zircons in them, are felsic enough to have zircons in them. That's not a plate tectonic environment in Iceland. That's a plume environment. And so the zircons they're not a tracer of plate tectonics. They're a tracer of a rock type. And then sometimes geologists are very good at this. We conflate rock type, or we take a rock type and say, oh, this rock type forms in this setting on the modern Earth. And so can we go back in time with that analogy, that link between tectonics and petrology or rock type? And I'm curious, Chris and Rachel, let me pose this question to you, because again, this gets pretty philosophical. How far back in time would you be confident taking a modern analog? We do this in geology all the time. We say, okay, on Earth, a stream has asymmetric ripples. So if we go back in the rock record and we see a sandstone that has asymmetric ripples, it means it's a stream. That's more of a physical one. But zircons and plate tectonics is kind of the same thing here. Like we're taking a link that's based on the way the modern Earth operates, and we're taking that back in time, or we take that to Mars, or we take that to Venus. Like how far back are you comfortable going?
Can you restate the question? Like you lost me 2 minutes ago. Oh my gosh. Holy. Oh my gosh. You're rambling like
maybe Rachel, you I'm rambling. Yeah, okay. Let's bring it home here.
Just
Jesse,
ask the question. What do you want to know? What's your question that you want to pose to Rachel?
I want to know how it's kind of like, Rachel, your experiments on, molybdenum isotopes. How confident are you in applying that to nature? Or are there other ways to form some molybdenum isotope signatures that you haven't thought of?
Okay, yeah. So that's what was going to be my caveat is we, like what you originally posed was like, okay, if we know that ripples form this way, then if we find them in the rock record, we know they mean this.
Yeah.
I think the caveat is it depends on how certain are we that we know that this is the only way that this thing can form in these rocks. And so that was, like my PhD research was trying to figure out what are the only ways that this specific molybdenum compound can be preserved in rocks. And if we know that, based on all these different ways that things can naturally happen, these are the only processes that cause this, then we find that in the rock record and we say, well, it had to undergo this process or one of these processes. So I think it depends on our confidence, which is difficult because if you run like 10,000 experiments, maybe there's something you haven't thought of. There are certain things, right, that we are pretty confident about. Like, okay, if I see a fish fossil in the rock, I'm pretty certain there had to be a fish there.
Yeah. Okay. Yeah. That's a good. Actually, that's a really good analogy. I like that one. That's like, for sure.
Yeah.
We're pretty confident in that.
Exactly.
There's no like random way to make a fish fossil, or that's a really random event.
Exactly.
I like the way you phrased that. Like, how confident are we that this is the only way to do it? But the point is to show that there's this big gray area in how you interpret different signals in the rock record. There are multiple ways in a non-plate tectonic process to produce zircon-bearing rocks. I guess that's the simplest.
That's what I was
answer the question.
Going to try and bring it back to, because I think, one, I think you bring up two very important points. One, the definition of when plate tectonics started is, and this is something I've mentioned many times in videos, is very hard to like say as a very specific number. It's always a range because global operating plate tectonics is different than like, okay, we see maybe there was a subduction zone, but how many plates were there? Was it just the one subduction incident? And then there's, still drift tectonics over here and there's rigid plates over here, but it's not everywhere yet. So there's this range of time in which plate tectonics was evolving on Earth at least from what I've understood. And we still have a lot of questions surrounding that range of time. And then the second major point I think you bring up is that zircon is something, and this is what I'm getting from the conversation. I might be wrong about this, but zircon is something that forms in slightly more differentiated rocks than mafic ones. So a little bit more felsic, it has to be. And I talk a lot about how felsic rocks or more differentiated rocks tend to form in continental crust, in continental settings, but that can happen in other ways. And that probably happened on very, very early Earth. That differentiation that allowed zircon formation likely happened before plate tectonics was the global regime, is what I think.
That's right.
That's why Jesse brought in Iceland, is differentiation is happening due to that mantle plume and the thickness of all those rocks there. So yes.
Yeah, that's exactly right. Zircons, and like I said, zircons occur in Mars, on the moon.
Yeah.
Okay, well, let's go on another tangent. Shall we?
Okay. So
that's great.
Briefly, I'm going to preface briefly.
Emphasis
in some of your podcasts, you talk about the moon forming impact and how there's some information there that you might be able to glean from these old rocks. So what do these oldest rocks on Earth tell us about maybe the timing of the moon forming impact or any other aspect of it?
Chris, take it away, my friend.
So I'll do my best here. Jesse, jump in. But when a Mars-sized object, roughly half the diameter of Earth, collides with Earth, that event is so cataclysmic that it's going to resurface everything. And that's going to reset the clock. Every rock, every mineral near and at the surface is going to be, the time is zero at that point. And so it's going to be exceedingly difficult to find anything older than that event.
So bring it home to the numbers, Chris, that we threw out, initially. 4.35 billion years old is the oldest zircon grain. 4.0 is we're confident in a rock being 4.0 billion. We're maybe confident in a rock being 4.25 billion years old. What does that tell us then that we have? So
the oldest zircon grains are going to be very closely tied to the time when Theia collided with Earth. That Mars-sized object did this and just resurfaced and reset almost every mineral.
Yeah, that's right. They provide a minimum number. And there's an interesting correlation between the oldest zircon grains on Earth, 4.35 billion years old, and a lot of dates for lunar rocks. The oldest dates for lunar rocks that are kind of like 4.25, 4.3, 4.35 maybe. Like there's a lot of slop in those numbers, but broadly, the oldest stuff is kind of in that 4.35 range. So some people would argue that that's the age of the moon forming impact, or that's the youngest that the moon forming impact could be, 4.35, 4.4 billion years old. Some people would say it's much older, 4.55 billion years old, or somewhere in there. But that's the limit.
Because you don't have plate tectonics on the moon, you don't have these resetting events. You have just these meteor impacts.
That was the reset. Yep,
right on.
I think that's such an important point because, as we talked about in part one, how we date Earth's age, its oldest age, 4.5 billion years ago, and it began to accrete along with the other planets in the solar system, is from non-Earth rock, is from meteorites, because Earth rocks have gone through resetting. And one of the oldest resetting event that we have was the moon forming impact, which reset both Earth rocks and moon rocks, which is really crazy. So that explains why the Earth's oldest rocks are not the age of Earth, is this moon forming impact, which is crazy.
It is crazy.
I mean, it's hard to imagine and amazing to kind of think about visualizing, like a planetary resetting event.
Right.
That is trauma that has been induced on the planet, just total resurfacing and resetting.
But it's cool too that we have not only these very old zircons on Earth, but also the entire moon that has preserved this timing and this, event. And also, you mentioned in podcast episodes that some of these oldest rocks on Earth have evidence for very, very early water on Earth, liquid water, I imagine, over 3.8 billion years ago, which is a long time ago. Because for those of you watching or listening that aren't aware, water, while it was around on Earth, it was not always liquid, because Earth very early on was very hot from formation and then very hot again from that impact. And so it had to, condense from water vapor from the atmosphere and then eventually formed our oceans. And so what do the oldest rocks on Earth tell us about when maybe the first oceans on Earth might have formed?
Yeah, we've mentioned 3 different rock locations. Acosta, that's 4 billion year old rocks. These rocks in Nouveau-Agatok, northern Quebec, that are mafic rocks that are potentially 4.25 billion years old, and then zircons that are older than that. In these really old zircons, going back to 4.25, 4.3 billion years ago, this was a really transformative 2 papers in 2001 where people measured the stable isotope, the oxygen isotope composition of those zircon grains. And oxygen's a great tracer of hydrosphere interactions, either liquid water interactions or low temperature water interactions. And these zircons contain a record of liquid water on the surface of the Earth. They have oxygen isotope ratios that are a little bit high. There's more 18 than the mantle, more 18 oxygen than the mantle has. So it's a geochemical inference. And then there's clear water lane sediments by 3.8 billion years old. So those are the 2 kind of pieces. And those are pretty well accepted ideas, I must say. Now, these 2001 papers were transformative, kind of threw the book out on our understanding of the early Earth at that point in time and said, oh, wait, no, this is kind of a cool early Earth where there's liquid water on the surface, where before we thought it was kind of like a hellscape. So,
wow. Yeah, I think that's super interesting. I actually have a video where I talked about when and how Earth got water and oceans. And I talked about hydrogen isotopes evidence that I had read about, but I didn't see the oxygen isotope evidence in the zircons. That's really, really interesting and older than what, I had, read about. So that's really cool. Wow. Okay. So speaking of water, do these oldest rocks give us any hints regarding the first life on Earth? I've discussed a little bit on my channel about, I don't know if you probably know all the old formations, but the Ischua formation of Greenland, and how I think it's like 3.9-ish billion years old.
At least 3.8. Yep.
Okay. And I've seen some, mention that it has some sort of stable carbon isotope evidence that might mean, very, very early photosynthetic life, but it's debated because they are deformed, obviously. So what's your take on this? Because I'm very curious. I've never had a good, person to ask about this. Is this true? Was there life that formed these carbon isotopes in these rocks? Or
so what's the evidence? The evidence comes from, a series of papers in the late 90s where people looked at graphite inclusions in apatite. In the case of Ischua, there's like these weird graphitic schists, these graphite schists that have apatite inclusions, or they have apatite in them. Apatite's a mineral, and there's an inclusion of graphite in the apatite. So the idea is like this apatite has kind of protected this graphite inclusion from metamorphism and later alteration. And you go in, you polish down into this tiny apatite grain very, very carefully. You expose the graphite. It's not necessarily graphite, but the carbon-rich inclusion in there, and you measure the carbon isotope composition of that. Those carbon isotope compositions are, you talked about, I'm sure, low. They're like, the values are low. The discussion or the debate comes in when we're talking about what is the meaning of these quite low carbon isotope compositions. There are a couple ways to produce very low carbon isotopes on Earth. One of them is life. Sedimentary organic carbon, which is life carbon, makes light carbon isotopes, makes low delta 13C values. Plant biomass is all really negative in this space, really low. So, if we had a granite on the modern Earth, and we measured if there's carbon inclusions in a zircon in a granite that melted some sediments, and we saw a minus 25 value, you'd be like, okay, there's life-based carbon in that zircon grain, because we kind of know a lot about the Earth at that time. We're kind of doing the same thing back in time. We're saying, okay, we see that same signature, that same chemical signature. Does it mean the same thing? Does it mean that there was life around? It depends who you ask.
Are you saying that just because you have the building blocks doesn't mean that you have the life, right?
So not just the building blocks, right? So I'm just going to briefly. I have videos on my channel talking about, the carbon isotopes and what they might represent in ancient rocks. But essentially, we've been talking about radioactive isotopes, how they decay over time, but there are stable isotopes that don't decay over Earth timeframes. And so because they're stable over time, we can take ratios of stable to stable isotope and get an understanding of what that means in terms of ancient climate and life. The reason we can do that is because these isotopes differentiate themselves or fractionate themselves differently in different environments and life forms on Earth, depending on their mass. And life that takes carbon from the atmosphere or ocean things like photosynthesizers that take up carbon dioxide from the atmosphere. They preferentially take up light carbon, carbon-12 instead of carbon-13 isotope. And so because they do this, they end up preserving, when they die and get preserved in the rock record as organic carbon deposits, they end up preserving a very light or carbon-12 rich signature compared to your other, inorganic carbon deposits that preserve a carbon-13 to 12 ratio that is not preferentially carbon-12 rich. Yeah. So they end up forming these really light or low carbon isotope ratios, which we see in these very, very old graphite, formations. But it's one of those questions, again, I think is, do we know for sure that that is the only way, that life is the only way that we can get this preferentially light carbon signature? And
that's exactly the key. And I'm curious what both of you think about this. And Chris, I want you to answer this question now. Because if you had a modern rock that had this exact same thing, there would be no discussion. We'd just say, yeah, okay, there's biological carbon in that graphite inclusion. Because on Earth, we know that making these light carbon isotopes in the modern Earth, life is the dominant way that it happens. And so, Chris, I'm curious what both of you think. How far can we take this modern analogy, this modern process? How far back do we confidently use that? Because some people propose and say, yeah, we have minus 25 carbon isotopes in these graphite inclusions. It means there's life. And some people would say, no, there's no way. That doesn't mean that, because we don't know. There's other ways to produce this light isotope signature. You can't say that with any confidence. We need more evidence to say that there's life on Earth. And I don't know where I stand on this. We're kind of saying, is time a variable? Should we change our interpretations only based on time? I don't know. Maybe it's not an interesting point, but it's
no, I think it is.
I can see where there's discussion. I can see why people disagree about this.
Yes, but I think we tend to have a lot more rocks and a lot less deformed rocks when it comes to much younger rocks. So I think if we were to find a rock that is 50 million years old, which is very young on geologic time, and see the same evidence, I don't think we would immediately jump to the conclusion of life either. I think it's less so time and more so it's not enough.
I see. It's amount of evidence. It's other rocks.
I think that's what it is. I think it could be wherever on the time scale, and we'd still be questioning it just because, okay, but are there fossils? Are there any other indications that there was life there? If we were looking at this 50 million year old theoretical rock, trying to decipher whether this isotope signature means life or not, I think we'd still have hesitancy using just that as for sure
That's
evidence.
A really good point. Yeah, it's not time. It's actually
I think it's the amount of evidence. And I think
that's true.
Where there are ways around this. I think that if we do a lot more experiments, if we try more ways and we consistently show that we need life to form this signature, I think we can get better confidence around this. But I do think it's one of those things that we will never fully obviously prove because we can't test everything. But we can get a lot more confidence the more things we test. That's my idea.
I think the isotope ratio, what you said, Rachel, is, I don't know a lot about it. In terms of this specific example, it is so cool. It really is. That's exciting to me.
Right?
It is. That's amazing science. And it's just the way that it all comes together. I don't know how else to say it. It's exciting. And that's really cool. So thank you for that. Yeah, Jesse, I have no idea. In terms of, I think, Rachel's right. You have to have more than one tool in the box.
It's a difficult thing. I think it's a little bit frustrating for people to have the answer of, I know Chris gets frustrated with me when it's when my answer is inevitably we don't know. There's a debate. There's a discussion. I think this is
you doctors need to figure this stuff out. That's how I feel. I'm like, you guys, come on, let's go.
Yeah, what are you doing? Sitting around there in your offices all day, figure this stuff out. But I think that this is a place where this is a healthy debate. You can see both sides. I can see both sides of this coin. I don't have any opinion about when the life formed on Earth. I don't. If it's 3.8, great. That's cool, but I'm not sure if is this the evidence for that? I don't know. I
have a question for both of you, actually. Then, so where are we with the banded iron formations, the BIFs? Because I know that a while back these were intimately related to photosynthetic deposition. Is that still the consensus, or where are we at with this?
That's a great question.
Okay, we're still there. We don't know. What is your personal thought? Are BIFs related to photosynthetic?
Yes.
Okay.
Yes. I think we have the right idea when it comes to BIFs representing kind of that first major oxygenation event. We had initially interpreted the termination of BIF formation as like, okay, well, let me just back up a second. Oxygen, O2, not the element. I always get people like, but oxygen was around at H2O. And I'm like, no, O2, I'm sorry. Molecular oxygen. Wasn't around always on Earth. It wasn't until photosynthesizers evolved. At the time, algae, not plants. Bacteria, actually. And they began to take up carbon dioxide and water and split the water and form O2, molecular oxygen. And this was, well, again, we can talk numbers, but it's a range. Maybe 3.9 billion years ago, maybe 3.5. But they began spreading very, globally and producing tons of oxygen and caused this huge increase in oxygen around 2.4 to 2.1 billion years ago. And this caused this big rock deposition of these banded iron formations. These banded iron formations represent oxidized iron deposits because back on early Earth, before oxygen was around, all the, chemicals on Earth were very reduced, meaning they had lots of electrons, and oxygen is a thing that loves to take electrons. And it went around and took everybody's electrons by reacting with them. And so iron was very reduced. It has lots of electrons. And so oxygen wanted to react with all that reduced iron. And it did, and it formed all these iron oxides in these banded deposits. And then we initially interpreted this abrupt termination of BIF deposits around 1.8 billion years ago as, okay, oxygen went around and pretty much reacted with all the, abundant oceanic reduced iron that was there. And it's now building up in the atmosphere and in the oceans and, we're oxygenated as a planet. Later, we went back and reinterpreted that less so as, okay, oxygen's building up on its own now and it's reacted with all the iron, and more so as actually there was a period in which oxygen went up, did all that, those reactions, and then rebounded, and the oceans the deeper parts of the oceans became relatively low in oxygen content again, and actually very sulfuric, because that initial oxygen event, the oxygen rise, caused a ton of continental weathering, because oxygen reacting with the continental rocks led to a bunch of continental weathering. And that continental weathering, and this is a long tangent, but I love this topic. It led to the transport of a ton of oxides like sulfate to the ocean. Sulfate is a sulfur oxide, and sulfate feeds anaerobic microbes that don't like oxygen. It feeds anaerobic microbes that produce hydrogen sulfide. And hydrogen sulfide, when it built up in this massive amount right after the GOE, the Great Oxidation Event, it terminated BIF formation and caused, instead of iron oxides, it caused iron sulfide deposition for another billion-ish years. And then we had the next Great Oxygenation Event and the Neoproterozoic one. And then oxygen was pretty much all around, and the ocean was never really anoxic and sulfidic ever again. It had moments, anoxic events, but it was never like globally, stably like that again. But there's periods in which BIFs kind of formed before they were supposed to form and formed a little bit after when they were supposed to not form. So there's like other deposits that are less well understood in terms of why they were forming. But it's also, there's local variation. And so sometimes it's hard to determine what's global, what's local. You kind of really have to drill down into the specific chemicals in there, because there are some chemicals like molybdenum. Now I'm really going to go on a tangent.
Hold on. Before this tangent, can I just interrupt and say, this is really cool. I've never thought about that before. This like oxygen making a lot of weathering and throwing sulfate in the ocean.
Yeah.
The Earth has so many amazing feedback loops to it that are just like, if you turn one knob here, it does this thing and changes the ocean chemistry. That's crazy. I've never thought of it or heard of this sort of this way before. So sorry to interrupt your tangent, Rachel.
Well, Rachel, hold. I'm sorry. I'm going to jump on this a second.
Go for it.
So
Stop
isn't
me.
this? No, I don't want to, because I love this actually.
Yeah.
Isn't this though another tool in your carbon isotope toolbox? Like,
yes,
this adds to it, right? I mean, so it's not just singular.
Yes, that's true. Actually, I should have mentioned that before. It's the carbon isotopes in the issue of formation are kind of, I think, the only thing that really indicates life to us. I actually don't know any, specifics about what's been measured about the Ishua, but in general, when we go and measure the chemistry of a rock, we tend to, especially if you find something interesting like that, we tend to measure lots of different proxies, and proxies are just like signatures in the rocks. And the specific proxy that I studied for my PhD was molybdenum, specifically molybdenum sulfides, which are really great at reconstructing or helping us understand better those past ocean anoxic periods. Those periods in which the ocean either became depleted in oxygen or never had it to begin with. So yeah, molybdenum is just another example of one of those tools or proxies that we can use. And we have a list of, you look at the periodic table, probably like 80% of those elements we use to some capacity like that. And so it's pretty incredible how much we can do. And each one says something different, like slightly different, but complementary. So it's really, really incredible what we can understand. Life is one thing that we can try and look for, but the chemistry of the ocean and the climate and the atmosphere, this is why geochronology and radioactive isotopes aren't the only thing,
Thank you for saying that. Yes.
So, thank you. That's true. It's true. All geochemistry is amazing.
Yes.
Rachel, can I ask you a question about the life thing? What's the oldest evidence for life that you're confident in saying, that's most likely?
Yeah, I tend to tell my students that we have potential evidence for life around 3.9 billion years ago, but it's more likely, and we have slightly more robust, more fossil cyanobacterial stromatolite evidence starting around 3.5 billion years ago. And then obviously it gets even more robust as we go younger and younger. But I think that is somewhat robust, not globally, but at least local evidence.
Yeah, I would agree with that. That's kind of the same. That's the same opinion I have is 3.2, 3.3.
Yeah,
we're pretty confident those are microbial mats and like the Strelly's pool in Australia and stuff like that. And then when you get back to the Isua, the carbonized substance Isua, or even the graphite inclusion in a Jack Hill zircon, it's like potential evidence for life. Is it diagnostic? No, but it's possible that that's life. And my understanding, this loses me. I have a minor in biology, but Chris and I both of our fathers are biologists, and so we grew up in a biology-centered household, and so therefore we do not like biology.
Really? I grew up with hard rock geologists, and I was like, I like biogeochem, low temperature, soft rock.
That's great.
Biogeochem.
That's great.
So I completely went the other way too.
We're always trying to raise the point that geology controls the biology ultimately.
For sure.
And vice versa.
Biology
sometimes.
attempts to always cover up our geology.
Yeah, that's right. It always gets in the way. All this lichen and trees and stuff getting covering up the rocks.
That's true. But sometimes microbes do affect the rocks that do form and how they form and their chemical composition. So it goes both ways.
The molecular clocks, though, I think the molecular clock people sort of say that 3.8 is no problem to have life.
That's true. The genetic stuff is actually really, really impressive. And I don't understand it well enough to teach it, but that stuff is like, because I tend to go by rock record, but the genetic clock, they match really well with a lot of the rock records. So it's got a lot of, well backed up stuff, but I don't understand it well enough to.
I don't either, but those people who do that stuff say that 3.8 is not a shocking number for there to be life on Earth.
Well, so on that point, just really quick, because you mentioned how you also kind of go by the 3.5, 3.3, 3.5. But what I like to point out to students when I talk about that is when we talk about the potential progression of the first, life and the evolution of life on Earth, we tend to talk about these cyanobacterial mats having evolved from a series of likely bacteria and archaea, very early primitive organisms that then eventually evolved to form these communities. So this life, although our first fossil evidence represents something that evolved from something that was older. So it's most likely not the first life on Earth, even if it is our first fossil evidence for life. So that's just one caveat that I think is important to remember.
Yeah, for sure.
Okay, so I'm going to skip down to the very kind of like rounding out questions. So what are some of the biggest questions about Earth's oldest rocks that remain unanswered? I know we hit some of these. We talked about how the plate tectonics question and how zircons were forming on early Earth is still obviously, actually everything we talked about in this part 2 is pretty much open. But what are the biggest questions that remain that if, a student is listening to this and they want to go into this research or look into this, what should they look at?
I would expect, I'd be shocked if there were not as old, if not older, rocks and minerals out there that we just have not discovered yet. And I think exploring for old rocks is really hard and time consuming and like massively expensive in these remote areas. So having new ways to do that, like coming up with unique ways to explore for old rocks would be one way. Just find more. Like if we have more rocks, my entire PhD thesis could be disproven by finding a couple more rocks in Acosta that, are different than the signal that we saw. So finding new ways to find old rocks or coming up with creative ways to do that is certainly one of them. Scientific questions, like you said, it's kind of an open book. Like pick which one. It's easy to kind of think, to focus on what we don't know. But we do know. What do we do know? We do know that there are rocks there. We do know that we have some of these samples. We're pretty confident that there was liquid water on the surface of the Earth. And we do have rocks that are continent-like. Let's say that.
Yeah.
The zircons at least look like they're from continent-like material. So big picture questions, I would kind of have 4. What was the volume of continents on Earth? What percentage of Earth was made of continental crust at that point in time? Kind of tied to that is plate tectonics. Was plate tectonics around and operative and active? Like was water getting pulled down into the deep Earth and doing melting and all those really important things? Was carbon being cycled down a subduction zone system? Was there life on Earth? We need, more evidence of that, more carbon isotope measurements and things like that. And then another one for me is how much land was exposed above the surface of the Earth? How much land was exposed above the ocean surface, so exposed to the atmosphere? That's a really important thing for a lot of Earth processes. And so that's an open question as well. We know there's at least some because there are some sediments there, but how much?
Yeah, that's such a good point, Jesse, because the Jack Hill zircon you said was deposited, 3 billion years ago?
Yeah.
That means that we had a significant amount of land above sea level at that point.
Yeah.
That's just, it's shocking to think about,
Is there anything else you want the audience to take away from our discussion about Earth's oldest rocks?
Chris, let me ask you this, Chris. Let me ask you this. Do you teach this stuff differently now than you did when I was a student?
Oh.
Do you teach more about the early Earth, or do you teach different aspects?
I teach it way differently now,
okay.
Jesse.
Yeah.
Absolutely. That was 20 plus years ago, and
sure.
If I was still doing the same thing now, then there's something wrong, because we've come such a long ways in that amount of time. So 100%,
okay.
Absolutely. But it is one of my favorite things to teach.
To teach.
Yeah, absolutely. Okay. Yeah. Yep. Jesse, what's the age of the Earth?
4.5 years old, Chris.
No. Don't take it down to the decimals. What's the age of the Earth?
4.5682. I mean, that's the age of that's
incredible.
That's the age of the start of the solar system. So Earth was 10 million years younger than that starting. Accretion probably takes 40 million years, 20 million years, something like that. So you can change some of those last decimal places, but yeah.
But those last decimal places, those are recent. They've 20 years ago, we wouldn't have been able to come to that accuracy, and that's so cool.
Yeah.
Cool.
I love that.
Very cool.
I love that as well. I mean, I love that you guys I love the whole conversation. I think this was really, really fun. I didn't know we were going to get so much into, life and this was, and that was great for me. So
yeah.
That was I also
awesome.
love that we highlighted at the end, how much we know, but also how much we still have left to discover. And obviously, as the age of the Earth has changed over time, we continue to constrain these things so well and so much better, and we continue to find new old rocks. So I think that's really, really amazing. And I think it lends a lot of opportunities out there for any student who's listening who wants to go work in this. Contact Jesse.
Or any number of other people working on it.
Yeah.
Rachel, if your listeners have questions or you have questions, I'd say we're open to part 3 and 4 and 5 and 6, because I think
I was going to say
didn't get to some of the questions. This is a super fun conversation. I mean, we could just keep talking about this and put a whole series together. I'm really curious, to know what your listeners' questions would be about, because we know from our podcast listeners what questions they ask us about the early Earth. And Chris and I both know from students, but you have a big YouTube following with a bunch of different
maybe
people who probably.
Okay, so anybody who's still listening or watching, comment. Well, if you're on YouTube, comment down below all of your questions, your follow-up questions from part 1 and part 2, and we will make a follow-up answering your questions.
There we go. Perfect. Sounds
great.
I'm
sure we'll get a lot, because I think I'm going to re-edit this, and as I edit, I'm going to be like, what about this?
What about that one?
So, and I had questions too that, we just didn't get to. I mean, this is something I know we could talk about the whole, day. But
Yeah.
I really think this is a great start, at least. And I can't believe I've never touched on this topic on my channel before, but I was so glad that you guys were here for me to do it the first time. And
Well, thanks for having us.
yeah, of
This
course.
is
And
great.
with that, please let people know, where can they find you? I know you mentioned it in part 1, but remind people, where can they find you and where can they listen to your stuff?
Yeah, our podcast is called PlanetGEO, so you can search the PlanetGEO podcast on all your podcast platforms. You can head over to our website, planetgeocast.com is our website. And we also have a mobile app where we have visual podcast series. That's called the Camp Geo mobile app. So you can search that in your app store and find probably a link to that in the show notes as well. And we have a bunch of audio, basically podcasts with images, with little images and GIFs that show what is an isochron, what does the oldest rocks look like, just simple images like that. So you can find us at all those places.
Well, thank you so much again for coming on. And
Thanks for having us.
Thanks. It's an honor. This is great.
Yeah.
Happy to be here.
Yeah,
Happy
I can't
to
wait
do
for
this. Great.
part 3, 4, and 5.
Me too. Absolutely.